All right, now the first thing I want to talk about during our debrief is this scatter plot and line of best fit. Okay. Now we've been using the phrase line of best fit fairly loosely. The official name for the line of best fit is called the least squares regression line. Okay, let's write that in here. Least squares regression line. And we just abbreviate that LSRL for short. Yeah. Now, let's talk about how it gets its name. Okay. So we can kind of assess how well a line fits the data by first looking at the residuals. Okay. So what are the vertical distances between each point and the linear model? Okay, very small distance there. Okay. And then you might think, okay, let's make a little key here. So this little vertical line represents a residual. Okay. So it would kind of make sense that if we just kind of add or sum up all the residuals, we can then get a measurement for how well the line fits the scatter plot. Okay. The smaller that sum, the better the fit. Right? But the problem is that some of these residuals are negative and some of the residuals are positive, so that if we just add them together, they'd cancel each other out. And we'd just end up getting 0 regardless of how well the line fit. Okay, so we need a way of getting around the fact that there's positives and negatives. And we do that by squaring. Okay, so we're going to look at the square of the residuals. Okay. Now, the cool thing about this is we can actually visually represent it by forming a square out of each vertical segment. All right, so we can form a square there, square, barely a square, square, small square, big square. Okay. So now each square that we've drawn, some are big, some are small, represents the square of the residual. And now we can think about area, right? Area is always positive, and we can look at the total area of these squares. Okay. Now, the best fitting line is going to be the one that minimizes the total area of these squares. Okay. And that's where we get the phrase least squares regression line. Okay. It's the regression line that minimizes the total area of these squares. Okay. All right, so that was just kind of some historical information about where the name least squares regression line comes from. All right, now let's go ahead and get to our questions. So I'm going to start here with question number, let's just skip straight to number 5, right? Questions 2, 3, and 4, you're just calculating stuff. Right, these are your plug and chug style questions. Here we're just finding the residuals and then adding that information to the mostly completed table. Okay. All right, so now we make this graph where we are putting the residual value on the vertical axis, and then our explanatory variable year is going on the horizontal axis. Okay. Notice how there's a line here for 0. Okay. So all of our positive residuals are going to fall above this line. Okay, so this is when the actual value is greater than the prediction. And then all of our negative residuals are going to fall below the line. Okay, this is when the actual value is less than the predicted one. Okay. All right. And so we notice that we start off with positive residuals and then have like 5 in a row negative residuals and then end off with a couple more positive ones. Okay. And because of that, there is actually a pattern here, right? There's a curved pattern, okay, in those residuals. Okay. So if you didn't catch that, go ahead and write that down for number 7, right? We have a kind of a U-shaped parabola. Okay. Now that's not good, right? It means that a pattern still exists in our data, right? The model that we fit here didn't capture all the pattern. It captured some of the pattern, but it didn't capture this curve pattern. It's left over. Okay. So what that really means is a linear model probably is not the best fit. We should probably go with a nonlinear model instead. Okay, now, what type of nonlinear model? I couldn't really tell you. Maybe quadratic, maybe cubic, maybe exponential. All that we can really say at this point is that a line, a straight line, is not going to be the best model. All right. So here at the bottom of the page, let's add one more little tidbit of information, and that is, okay, if the residual plot had shown no pattern, right, if this just looked like random scatter, okay, then that'd be an indication that the line was a good model and there's no leftover pattern remaining. All right, so if the residual plot has no pattern, okay, meaning it just looks like more or less random scatter, okay, then the line is a good model. But if you see a pattern, it means the line did not capture that pattern, and so the line's not the best model. All right, so yeah, not a whole lot to write down on the front page. Let's move on to the back page and we'll do a summary of the most important ideas, starting with that acronym LSRL, okay, which stands for Least Squares Regression Line. Okay. Now we can draw all sorts of lines on a scatter plot, some good, some bad, okay? But the best one is going to be the one that minimizes the sum of the squared residuals. Okay. Or visually, it's going to be the line that minimizes the total area of those drawn in squares. All right. Now, one way to tell whether a model is a good fit for the data or not is to look at a residual plot. Okay. A good residual plot is going to look like random scatter. Okay, it means that all the pattern's been captured by the model. Okay, but if you're seeing a pattern still in the residual plot, okay, then the line wasn't a good fit. It didn't capture the entire pattern. So things to look out for are kind of smiley faces or frowny faces, any kind of curve. Okay, another thing to look out for is a residual plot where the variability gets wider, right? So it kind of widens out as you go left to right. That's not a good one either. Okay. All right, so depending on the time, we might need to stop here, but if there's still time left in the period, you can go ahead and work the check your understanding questions with your group, and then I'll post an answer key on Canvas later this afternoon.